Great. So we talked about sorting vectors last time, including using the function sort, which just puts the elements of the vector in order, as well as using the function order, which tells us which items we need to grab from the original list in order to obtain an ordered list. So for example, if we do order of 72, 45, 100, then it's going to return the vector 2, 1, 3. And that's telling us we need to grab the second entry, then the first entry, then the third entry if we wanted to have a sorted list. And this is enough to allow us to sort a whole data frame according to the values in any particular column. So you choose a column to sort by, and you can sort the entire data frame, not just that one column, using the order function. So I'll give you a little bit of time to see if you can remember how this is done, put together a couple of ideas here. So the prompt here is to write a few lines of R code to sort the whole murders data frame in order based on the number of gun murders. So that's the total column. So a few folks are getting their answers in, they're taking some time. So what I'll do is work this out over here. So the first thing we want to do, as suggested, is look at the total column. And we want to know how to sort these. And if we just call sort on this column, then we'll just get the values in order and we won't have any information that we can then go use to sort all the rows of the data frame. So what we want is the order function, and we'll store that in a variable which we'll just call index. And that looks like this. So this says the 46th row contains the smallest element and so on. So if we index the data frame's rows with this vector, then we'll be putting the data frame in order according to that column. So as we learned in the first or second day, we can use single brackets and index a data frame as if it were a matrix. So we can do murders of index comma, and we want all of the entries here. So we can just leave that blank and it will grab all of the columns. And this did what we want. We have the values in order now in this last column, and all of the other entries in the data frame stayed in the appropriate row, so things don't get mixed up. So this is just a message indicating the same thing that we just did, so that you have that on record. Okay, another thing that we talked about last time is the NA value, which stands for not available. And I want to do a bit of practice with that. So you have an example called NA_example in the DS Labs package that we've now loaded. And you can count the number of NAs in that example. So this is a small exercise as well, although there are quite a few hints here. So the function is.na will help you check whether each value is an NA or not. And you can apply the sum function to a logical array to count the trues. So just practice that a bit, apply these two functions to count the number of NAs in NA_example. Okay, so while people continue to get their answers in here, I'll work this one out as well. So in a example, as we said, it looks like this. And what we can do is apply the is.na function, which is vectorized. So it works, if you call it on a vector, it applies that function, the function which checks whether something is a not available value, to each entry of the vector. So if you run this, we're going to get a bunch of trues and falses, with falses everywhere it was an actual number and trues everywhere it was an NA. And then in computer science, we typically think of true as 1 and false as 0 for arithmetic purposes. So if we call sum on this vector, it counts each of these trues as a 1 and each of the falses as 0 and totals up the results. And that will produce the total number of falses. And so we see that, sorry, the total number of trues. So we see that it's 145. So, you know, you could count them by just moving through this list, but that would be pretty tedious. This is an easier way to do it. Okay, so let's move forward then. So California had the most murders, as we saw, 1,257. But does this mean that it's the most dangerous state? What if it just has more people than any other state? So let's write a line of our code which returns the name of the most populous state. So remember that the population column is called population and the state name column is just called state. All right, nice job. Lots of folks got this one, or several folks. Maybe other people are still working on it. So this is a bit of a review from last time. So the idea is that we can do which dot max to get the index of the row with the biggest state. So like if the third row is the biggest state, we get a 3 out of that. And then we can index the murder's state vector with that value, and that's going to tell us the name of the state in that row. And we find that it's California, which is not surprising if you know some facts about state populations in the United States. So that seems to be working fine. So in particular, California has over 37 million inhabitants, according to this data frame. And so it's unfair to compare the totals if we want to know how safe each state is. So what we really want to be computing is per capita murders rather than just murders outright. So we want to normalize by the population. We want to divide the murder totals by the populations in order to get a more apples to apples comparison. All right, so the way we're going to do that is take advantage of the vectorization of operators in R. So suppose we have some values, 69, 62, and so on. We create a vector of them and assign them to a vector called inches. So these are representing the inches for some measurements that are being made. So we have 10 observations here, and they're being stored in this vector. And suppose we want to convert them to centimeters. So what you might like to do is multiply each value by 2.54. You might think, okay, I need to figure out a way to do that, maybe with a loop or something. In fact, you don't. You can just multiply the vector, the variable storing that vector. You can say that times 2.54, and this operation is automatically vectorized. So each value gets multiplied by 2.54. Likewise, if we wanted to subtract 69 inches from every value, we can do that just with a single subtraction operation, and that is going to automatically vectorize this operation. It's going to subtract 69 from every value in the inches vector. So this first entry, which was 69, goes down to 0, and so on. Everything gets 69 subtracted. So this in both cases involves a scalar, or in other words, a number. So 2.54 here, or 69. If we apply these operations with two vectors, it likewise will perform that operation on an entry by entry basis. And specifically, it will do that by, let's say, if we want to talk about vector addition, it will do that by adding each entry. So if we add ABCD to EFGH, we're going to get A plus E, B plus F, and so on. All right, and similarly for any of these other arithmetic operations between two vectors. Incidentally, for those familiar with other languages, if you're used to Python, this is how NumPy arrays work. And if you're used to Julia, then these operations are what we would denote point times or point divide. So if in Julia, you have to specify that it should be done element-wise. In R and in Python, you don't. It's automatically, all of these operations are automatically vectorized. Okay, so for example, if we want to compute the murder rates, we want to divide for each row, we want to divide the total value by the population value. And then we want to multiply this by 100,000 because we want the number's going to be really small, and it's sort of hard to think about really small numbers. So this says per 100,000, how many people are we talking about? This gets the number up to a kind of macroscopic value that we can look at and conceptualize more easily. But anyway, the point is we want to do this entry by entry. We want to take for every row, we want to take its total value, its population value, and divide. And then for every one of those values, we want to multiply by 100,000. And so we can do this in this very straightforward way in R, but just by putting the slash for element-wise division and the times for element-wise multiplication. So we get numbers that are much less disparate than the original numbers. So some values are like 2.82, some values are as big as 3.45, or maybe a bit bigger than that, but we don't have this sort of huge gap between numbers like 2 and numbers like 1257. Okay, so once we do this ordering, we see that California is no longer near the top of the list. So if we look at the state abbreviations and order by murder rate, then we're going to find Vermont is still at the bottom, but now DC is at the top. So this is quite a different ordering than the one that we had before. And that makes sense because that one included population, sort of conflating murder rate and population in a single number. And now we're starting to separate that out. All right, here's an exercise. Suppose that we have some temperatures in Fahrenheit and we want to convert them to Celsius. So come up with a vector that contains the temperature of the following cities in Celsius. So no one has their answer in yet. So we'll do some more time on this one. Take another minute or so. Okay, so here's my solution. So we're going to apply this formula, 5/9 times f minus 32. We'll use parentheses in the same way that we did in the math expression to group this operation so that it happens first. And then I also called the round function in case we want to make sure the temperature values are integers. Of course, this is not really part of the prompt, but I just included it so you can see this function. So I'll share some of the answers that were produced in class. So nice job with these. Yeah, so some folks grabbed the column from the data frame rather than using the original variable name that we stored, and that's also completely fine. So here's another very common operation with data frame types. So suppose that we've calculated the murder rate as we've just done, and now we want to take it to another level. We want to sort of check which ones of these values satisfy some criterion. So to put a specific situation to it, imagine you're moving from Italy where the murder rate is 0.71 per 100,000, and you'd prefer to move to a state with a similar or better murder rate. So what we can do is do murder rate less than 0.71, and this mathematically, it looks like it's comparing a single number to another number, but in R, this operation is vectorized. So this less than operation will check less than 0.71 for every entry of murder rate, and then return a vector of logical values, which says whether that number is indeed less than 0.71. So we get some falses where it's not and some trues where it is. If instead we'd wanted to know whether it's less than or equal to 0.71, we can use the less than or equal to operator, which kind of looks like this arrow here, but you can just read it one character at a time, less than, equal to. And then we'll apply the following technique once we have this vector of Booleans. If we index a vector with a vector of logicals, it will keep all of the ones with a true in the corresponding position, and it will drop all of the ones with a false in the corresponding position. So this is our way of subsetting the data set to see which states have murder rates less than 0.71. And here they are: Hawaii, Iowa, New Hampshire, North Dakota, and Vermont, just those 5. So if you read through this vector, you're going to see that there are only 5 values here, which are true, and all the rest are false. And if we do want to count them, as we saw earlier, we can apply the sum function to this logical array, and it says what we can see with our eyes here as well, that there are 5 true values there. Okay, so suppose we like the mountains and we want to move to one of these states, which is also in the western region of the country. So we're applying an additional filter here. We want the murder rate to be, let's say at most 1. So we'll relax our 0.71 from a moment ago. But we also, in addition to that, we want the state to be in the West. And we have that data available. That's one of the columns, so we can take advantage of that. And the operator that we want to take 2 logical vectors and combine them into a single vector, which says in each position are both values true. So that is the AND operator, which is a single ampersand in R. So this is a vectorized operator but it also applies to individual values. So if we do true and true, that's true, but any other combination is going to be false. So what we'll do is define a single vector here, which we'll call west, which says, is the region for this particular state equal to west? And we'll define another one called safe, which says, is the murder rate less than 1? Rather less than or equal to 1. So if we look at these values, west has some trues and falses, safe has some trues and falses, but in different positions, and we want to figure out where are they both true. So that's going to be the ampersand applied to these two vectors. And again, this is a vectorized operation. So this is going to do it entry by entry, which is exactly what we want here. And we get these 5 states. So Hawaii, Idaho, Oregon, Utah, and Wyoming. So once again, here we're using this logical vector stored in the variable name IND. We're indexing the state vector, which has 51 entries in it, with this length 51 vector. So you can see these 51 values. We're indexing the state vector with those values, and that's going to drop all the entries corresponding to a false value and keep all the ones corresponding to true. Okay, so here's another helpful function in R. It's called which. So suppose we want to look up California's murder rate. So it's convenient to convert logicals into indices to do this sort of thing. And the which function allows us to do that. So if we do murders state equals California and then call the which function on that, it's going to tell us where the true values are. So we can then use that index on the murder rate vector to find the corresponding entry there, the one that corresponds to California. Now, this works just fine even if we delete the which function here. So I'll show you the IND value so you can see what I mean. So when we just called murder state equals California, we got a bunch of falses and trues, but of course there's only one California, so there's only one true, and it's in position 5, 1, 2, 3, 4, 5. And so this index value here, it only contains that one value, which was true. So this operation works either way, even if we omit the which function. So what do you think would be a reason why we might want to store a vector like, let's say 258, rather than a vector like false, true, false, false, true, false, false, true, false, false? So what's the advantage of storing the indices of the true values rather than all of the values true and false? So I put a pretty tempting incorrect answer in here, which is this third one. So it might make sense to think that it's faster to search for a vector than an index logical array, because this is true for you with your eyes. If I ask you, is 5 in this list, you can look at it very quickly and say that it is, whereas here you'd have to count things out and make sure you found the correct 5 position and read what's there if it's true or false. But this is not true for a computer. So it is in fact much slower to have to search through a vector for a number than it is to jump straight to a particular value. So indexing a vector is extremely fast for the computer. It does not have to search through the vector at all. You can do C bracket 5 and it will grab that entry as fast as it will do anything else. Whereas here, if this vector were quite long, it might take several operations to perform this search to try to find the value there. So this is, I would say, the best answer. Okay, here's another helpful R function. It's called match. So if instead of just one state, we want to find out the murder rates for several states, then we can find these values using the match function. So this function tells us which indices of the second vector. So it's going to take 2 arguments, and it's going to tell us which indices of the second vector match each of the entries in the first vector. So if we do New York, Florida, Texas, and call the match function on murder's state, then it will return the indices for those 3 values in order. So the New York row is row 33, the Florida row is row 10, the Texas row is row 44. So here's another example, making sure that you can see really concretely how it works. Since of course we don't have this whole data frame memorized, here we can have it kind of all out before us. So we're calling the match function. So we're saying, tell us where 55 is, tell us where 20 is, tell us where 12 is in this vector in the second argument position. And so 55 is in the third position, so we return that first. 20 is in the second position, so we return that second. And 12 is it's not there. So we return an NA saying this is not available. You can use an optional argument for the match function to produce a different value here besides NA. So NA is just the default if it doesn't find it, but sometimes you might want a different behavior and you can specify that. Okay, so once we have that vector of positions, we can index the murder rate vector with that vector of positions we found, and these are going to be the three corresponding values. So New York, Florida, and Texas have murder rates of 2.66, 3.39, and 3.20. So here's yet another function that comes up a lot, maybe even more than the match function. So it's the in operator, and it's got these percent signs surrounding the word in. So this is an operator, the single 4-character thing. And what it does is it checks whether or not each element of the first vector is in the second vector. So the example given here is, suppose that you're not sure if Boston, Dakota, or Washington are states. You can answer all three of these questions at once by making a vector of the words that you want to check whether they're states, and then just asking, are they in murder's state, or are they in this vector? And you'll find, of course, that Boston and Dakota are not states and Washington is a state. So you'll get false, false, true here. So this in operator, like all of these other operators we're discussing, it's automatically vectorized. It's able to handle not only one value here, but many. So but you can also do it with just a single value like this. And it's very closely related to match. It's basically just checking whether the match function returns NA or not, some positive index value. And just a brief side note before we move on about this weird percent sign thing, because you'll see this a lot in R, especially as we move forward into using some of the packages that we'll get into. So the percent signs are very common. That it's R's way of syntactically denoting an infix operator. In other words, it's its way of saying that this is an operator that goes between its two arguments instead of before. So if we say, is the number 2 in the vector 1, 2, 3? Of course it is, so that will return true. We could also call this as a function in the ordinary way by surrounding this operator in backticks. So this is the character that's in the top left corner of your keyboard. And it's essentially the way of calling an infix operator as if it were a regular function. So this is kind of a lot of characters here. But again, the percent signs form an infix operator, and then the backticks take us back to being able to call it like a regular function. This is what it would look like with the function first, then the first argument, then the second argument, right? So this is the same thing here, but just a different style. So we'll see that quite a bit. It is worth maybe pointing out that not all infix operators require the percent signs. There are some privileged built-in operators like plus and times, where it would be very annoying to have to put the percent signs around them every time you want to use them. And so they don't require them, and they're parsed as infix operators no matter what. But all user-defined infix operators do require the percent sign. So there's a distinction here between things that are built into the language, or at least some of the things built into the language, and what you have access to do as a library author or as a user in your own code. All right, so here's an exercise. How many states have a murder rate lower than 1 per 100,000? So you can give me a number as well as the code, or either if you prefer. So as people continue to get their answer in here, I'll walk through it on this side so we can say murder rate less than 1. And that gives us trues and falses according to which entries have a murder rate less than 1. And then we can sum that. And we find that the answer is 12. Yeah, so some people are putting the 100,000 in. Remember that we included that in the definition of the murder rate vector. We went ahead and normalized it per 100,000 people. All right, so yeah, this is what we just worked out. There are 12 of them. I forgot to mark this one as an exercise, but here you go. So I'm from Mississippi, and people often get confused about state abbreviations because there are many M states. So write a line of code which uses the murders data frame to tell us what the abbreviations are for these 3 states: Mississippi, Missouri, and Michigan. So as people continue to put their answers in, so what we want to do is use the match function that we learned a moment ago to check for each state which position it's in the murders state vector. And so we see that these 3 states are 25, 26, and 23 respectively. So we can store that in a variable called ind, if we like, and then we can index the murders abbreviation vector with that index vector and find 3 abbreviations. And we see that Mississippi is MS, Missouri is MO, and Michigan is MI. Really, the trickiest one here is Missouri, because you would think it would be MI or MS looking at the beginning of the word, and in fact, it picks up this vowel. And the reason is that you have these 2 other states that have already claimed these 2 other abbreviations. Okay, so that kind of wraps up our basic vector manipulation portion of the course. We're going to move on now to doing some plots. So things will get a bit more fun for a moment because we'll see more action happening. There's more visual stimulation here. So what we're going to do is develop a new visualization package, or rather, it's not new. It's 15 years old at this point, but it's different than the one that's built into our language, and it's got a lot of things going for it. But we will talk a little bit here about how to use the base R plot functions, because there are some instances where you would want to use these functions instead of bringing in the library that we're going to learn. So, okay, so if you want to make a scatter plot in R, the simplest thing to do is just call the plot function with your X values in one vector and your Y values in a second vector. So it's a 2-argument function, and it's just a vector of X's comma a vector of Y's. So for example, if we want to do a scatter plot where we do population on the horizontal axis and total number of murders on the vertical axis, we can do it just like this: plot of X comma Y. And we find that indeed the bigger a state is here, the bigger a state is here along this axis in terms of population, the more murders it's going to have, generally speaking. There's a clear positive trend there, and that makes a lot of sense. A cool thing that you can do in R that really can't work quite the same way in any other common language is to use the function called with, which allows you to specify in the first argument a data frame, and then the second argument you can skip calling that data frame. So you can use a variable, which is a column in the data frame, and it will. So what R is actually doing here is it's going to check, is population an R variable that's in scope, and if not, then it will check, is population a column of the murders data frame, and if so, it will use that instead. So it's sort of giving you an extra context here that you can take advantage of. All right, so this is a little bit tidier, and it's not just the plot function that you can do this. This works with any function. So you can do width of data frame, comma, and then whatever, and that whatever will be evaluated in such a way that any variables that R doesn't find in its workspace, it will look up and see if there are columns in that data frame. Okay, so we can also make a histogram using the hist function, and a similar idea, except we only need one argument this time. So we call hist of any vector, and it will make a histogram of that vector for us. So very simple. And what we can see is that there's one huge outlier in terms of murder rate. So if we do total divided by population times 100,000 and store that as X, so this is the murder rate column that we computed before, we're going to get this one major outlier, but everything else is sort of, well, it's distributed roughly like this. A lot of values pretty low, a few values a little bit higher, and then this one way out here. So there's a question about the width function here. So would width be a problem if you had another variable called population outside of the data frame? So let's check it out. Let's just see how this would work. So again, this is the murders data set. We have this column called population. And if we run a line of code which just has population in it, it's going to say, this is a problem. I don't know this variable name. But if we say with murders population, then it will look up that variable in that data frame. So this is exactly what we would expect. Now, the question is, what happens if we assign some other value to the population variable and then try to do this same thing? What's going to happen? And okay, it looks up with the width function in particular, it will look this up in under the data frame first. And if it finds it, it will use that and it will ignore any variable names in scope. So this works fine. We'll see in other instances where there are tricks for using a data frame's column name and having it look it up automatically. There are some instances where this kind of stuff can get you in trouble, but this one is fine. So yeah, so this is a great question. It's fine, actually. And incidentally, if we wanted to look up that one outlier, I feel like if you look at this histogram, your main question is, which state is this one? And we can look that up by doing which.max to find the index of it. To find the index in that vector, which has the maximum value, and then look up the corresponding state. And what we're going to find is that it's DC, which makes sense because it's very small. It's completely urban, whereas every other state has more rural areas to balance out the higher crime urban areas. Okay, so here's another plot type, and this one does involve a little bit different syntax. So this is a new operator, this tilde here. So we'll just mention it briefly now because we'll be able to say more about what it means later, but this is part of how the Boxplot function is called. So we have to mention this now. So suppose, again, we store the murder rate as, in this case, let's store it as a column in the data frame. So if we just delete this second one for now so you can see what happened here, we actually added a new column. So if we assign to murders $rate, we will get a new column in our data frame. This operator here creates that. So we'll get a new column in our data frame, which represents the murder rate per 100,000. So we can then call Boxplot. And the way this function works is we need to supply which data frame we're going to be grabbing data from. So we're going to say murders is our data frame for this plot. And then we do rate tilde region. So this is specifying the Y value, this is specifying the X value. And notice this is a categorical variable. This region, it's a factor column. There's only 4 possible values here. And so on the X-axis, we'll just have those 4 categorical variables. And on the Y-axis, we have this numerical quantity, which is the rate. So it's just Y tilde X here is the style. And this could be done with separate arguments. You could just have a comma here instead of a tilde, but this is what was chosen when this function was created. In any case, we get a box and whisker plot. So what's happening here is we've got the quartiles here, and we also have some allowance for outliers to be plotted separately as their own points. So we have these 2 states which are within the South, which are kind of way outside the typical range that the other values are in. We can also see from this visualization that the South has higher murder rates than the other 3 regions. So just to clarify a bit what this tilde is doing, it's an expression which indicates a special type called a formula. So when you do rate tilde region, that creates a formula object in R, which it basically just, it's a special structure that sits around and waits for another function to do something interesting with it. So we can do rate tilde region, so you can see what that looks like, and it's not even doing anything with it. Each one of these values is not even defined. It's rate, if you try to make a vector out of it, it's like, what's that? I don't have that variable in my workspace. I don't know what you're talking about. But if you make a formula, it sort of holds it holds both of these names and waits for something else to happen with them. So that's why we didn't need the with function here. It's because this is essentially just kind of holding those values for a function to do something else with them. Like in this case, the Boxplot function is going to use its data argument as a context to look up these variable names and convert them into actual vectors in order to make the plot. You can also have formulas that just have the tilde like that. And if you want to check the type of this thing, it is of type formula. So this is a special built-in type that's designed for this purpose. Okay, here's another handy thing, kind of quick and dirty thing you can do in R. You can call image on a matrix and it will make a heat map for you. So let's consider this matrix, which starts in the top left, counting out 1 through 12, and then comes back up to the top to count at 13 through 24, and so on, all the way up to 120. We can visualize this matrix in this way, and that's totally fine for this one. But if we wanted also a heat map to kind of see where the larger and smaller values are in a more visually digestible way, we could call image on it, and it will produce this heat map for us. Yeah, so I think it's cool too. There are lots of handy functions in R that they're very simple to call and quickly give you something interesting that you might want, where you don't have to go pull up some library and make sure you remember how all of that works. You'll never forget how histogram works. It's just the hist function called on a vector. That's it. Same thing for image call on a matrix, and you get an image of that matrix. Okay, so we have just enough time for one more exercise, and then we'll be done. So population is strongly related to the number of murders. That's the scatter plot we just made. And it's not very surprising. It in some ways is not containing as much information as it should, because it includes this kind of obvious conclusion in it. So suppose we want to have a more meaningful visualization that tells us whether there's a relationship between population and murder rate. So we're going to pull population out of it on the vertical axis and get a little more signal. So what I want you to do is see if you can make a scatter plot with the base 10 log, so that's just the log 10 function, on the horizontal axis and the murder rate on the vertical axis. I'll share some answers that folks got here. So this is using the vector names that we came up with. That works. We can also index explicitly, so we can do log 10 of murders population. That's the X vector, murders rate as the Y vector. And we can also use the with function. So nice job all around there, providing me with several different examples to draw from. So here it is with the with function. And we can see that indeed it is a more informative plot. There's instead of seeing all the points sort of lying roughly along a diagonal line, we now have some separation, and we can really say, okay, there's this major outlier, and there's some slight trend upwards, it looks like visually here. But of course, we need some statistics to say whether this upward trend that you pick up with your eye is statistically meaningful or not. But at least in terms of the data visualization, we can see what's going on here a lot better than we could back higher up when we created this plot.